to lecture number 13 on network analysis, and we have been discussing about RL circuits excited by a time varying voltage source. And I told you that suppose you have a circuit like that and you have an RL circuit here. So, this switch, when it is in open position, there cannot exist any current. So, I 0 minus was 0, and then it was connected to this terminal at t equal to 0. Then what happens? This current will equation of this current, which is very popular and one should remember. Final current will be DC current, and it was like this 1 minus e to the power minus t by tau. Tau is an important thing which is called time constant, and it is the ratio between L and R. So, it is and the nature of the development of the current will be exponential in nature, and finally, it will reach asymptotically to this final value E by R. Of course, one need not wait for infinite time. After few time constant, it will be almost reaching E by R. Now, similarly, the question is, if suppose the same circuit I will draw here, understand the problem first, so that it will be easier for me to talk. So, this is the same circuit here, but here I make an arrangement where I connect some or say I will do like this better. I will connect a similar circuit. Here is a resistance R, and here is an L, and here is a load resistance R L. Okay. Switch is connected initially in position 1, position A at t equal to 0, at t equal to 0. Therefore, at t equal to 0, this is the equation, and current grows up, and thereby pumping current into the inductor. And inductor, when it carries current, we know it stores energy. Now, what I will do at some time, say at t 1 time. So, current started growing like this. Let me redraw this in this fashion. So, current started growing up in this way, following this curve, but suppose at some time t equal to t 1, say at t 1 time, what I do, I move this switch S to position B very quickly in known time practically. So, this switch is moved from position A to position B at t equal to t 1. Got the point? And then I will say that the circuit is, when time is between 0 to t 1, okay, circuit was like this. This was my IT, and it was growing in this way up to t 1 it will go, and for t greater than t 1, the circuit will look like this. This is R L, this is L. R L is the load resistance. Now, this example will show you that okay, you have stored some energy in the inductor. Now, that stored energy you want to use in some load resistance, for example, for heating purposes, or it may be a small lamp, whatever it is, whether it is possible. So, initial direction of the current, this current we were talking about, it was I t. So, expression of the current I t I will write for this problem. I am sure about this, that this will be E by R into 1 minus e to the power t minus tau, where tau is L by R, and this is valid during this time interval 0 to t 1. You may put equal values also, no problem. So, this is how current grew up in the inductor. Circuit did not know that at time t equal to t 1 you are going to do another switching from A to B. So, it was following this curve faithfully as dictated by this equation. Now, at t equal to t 1, S is moved from position A to position B. This is the position B. Here it was connected to position A. Position A to position B, small b, very quickly means practically no time is wasted to do that thing. That is what I will assume, practically in no time. I mean, here sometimes people feel a little uneasy, because you are moving it from A to B in no time, but it will take a finite time, no. So, there will be some time will elapse, during which time it will be open circuited. So, how I mean, with the help of solid state switches, this can be easily implemented. This you take it for granted for the time being. So, I am putting a condition, practically no time is very important. That is, as if circuit was connected to A at till t 1, then at t equal to t 1 it has got connected to B. Somehow you have made some arrangement very fast, I mean, so that this terminal never sees an open circuit existing during that interval. We will show you several examples where in practice this can be done. Okay. So, that is very important, in practically no time. If that be the case, then my problem was, by this two switching I want to find out the current for t greater than 0. So, for t greater than 0 means 0 to t 1 is already obtained. Now, the question is how this current will behave, the nature of the current variation for time greater than t 1. That is what I want to find out. Now, to avoid any confusion, what I will say that let t dashed be t minus t 1. T 1 is a fixed time, t is the time which is counted from the very fast switching I started. So, that is t, and let me define another variable t dashed, okay, which is this t, a time shifted thing, that is beyond this time. So, for t greater than t 1 or t dashed greater than 0, this is the circuit, same circuit, t dashed is this, and then I have to find out the current. So, I assume the current to be I t. This I t is either you say for t greater than t 1 or t greater than t dashed. So, I t dashed current flows. Okay. Now, then what I have to do is this, I have to write down the KVL equation here, and once you have assumed the direction of the current. So, the drop here will be, this is plus, this is minus, and this drop will be R L into I T dashed. This will be the drop with this polarity, and since current is flowing like this, the polarity of the voltage, as we have seen here, will be L d I dashed dt, is not d I dash, d I T dashed dt dashed. So, a new variable of time I have just defined. So, your KVL equation will be from minus to plus, if you go minus to plus L d I T dashed dt plus R L I T dashed, and this has to be 0 because there is no source existing. So, question should not be asked that there is no source, external source is connected, then why there should be current? Yes, current will be there because the inductor had some initial energy stored at t equal to t 1, is not. So, inductor, since it is an energy storing device, will store energy and can discharge energy whenever it gets opportunity to do that. So, this is how it will be. So, I do not bother. So, it is like this is the differential equation, and then I will solve it. I will solve it on this page only, so that you understand what is going on. So, like the previous one, I will divide it at d I T dashed dt, divide by L both sides. Let me do it very fast, R L by L. This capital L indicates load resistance, nothing else. R L by L I T dashed is equal to 0 here, no external source exists. So, this is the thing, and once again I will do very rapidly that you multiply this with the integrating constant R by L T dashed d I dt dashed, I am sorry I am forgetting this t dashed, plus R L by L I is equal to 0 into e to the power R L by L T into I. I have multiplied with this integrating constant, and then I get d dt dashed is equal to the product of these two functions R L T dashed into I, and that is equal to 0. Since right hand side is 0, I conclude that this must be a constant, because if you differentiate a constant thing, that only gives rise to 0. So, R by L T dashed into I is equal to 0 here, or I will say that not 0, a constant, say A. So, I T dashed will be equal to A into e to the power minus R L by L into T dashed, is not. This will be the solution. Now, the question is, what is the value of this constant? The value of the constant is to be found out, because you know that I T 1 from the previous example, it was equal to, from this circuit, it is equal to I T 1, that is at T 1, this value was equal to E by R into 1 minus e to the power minus T1 by tau, where tau is L by R, this circuit. And this will act as at t equal to T1, it is like this. So, I t dashed equal to 0 minus is this number is equal to I t 1, is not I t dash 0 minus. So, this is the thing. So, I 0 is equal to this I 0 minus and therefore, the value of the constant will be I am just writing I 0 minus this 0 is new 0 t dashed 0 is equal to this is t dashed corresponding to that t dashed 0 minus will be equal to A, and which is nothing but your I t 1 calculated previously. So, this number is known from which value of A is known. Therefore, the solution of the current I as a function of t dashed will be e to the power minus r by L into t dashed, that is the thing, and here this current will be current at I t equal to T 1, got the point. So, this number being known from this previous switching at t equal to T 1, you put that value and get this. Now, sometimes because these t dash t all things are existing, so you can express it as I at T 1 and e to the power minus r by L, and for t dash you write t minus 1. So, that your original t equal to 0 chosen is preserved in this equation. Got the point. So, but only thing is this equation is true for t greater than equal to T 1. So, if you now see what is going to happen, if I sketch it, it was growing like this is t axis mind you. So, at t equal to T 1 it went like this. So, this was the initial current when the second switching is done, and then that current will decay down to 0. So, this is t equal to T 1, got the point, and this is t dashed, everything is fine. Not really, because if you put t equal to T 1, what will be the current? It is indicating how much is the current. It is 1, na? So, I t 1, fine, good. So, this is I t 1. Anyway, this is the mathematical thing. Now, I allowed the current to grow up to this point I t 1, and then I did that switching. I better draw the circuit once again, so that you understand what is going on. This was your R, this was your E, and this is L, and then this is the switching R L. And then you close it here A to B, and this current we are solving, mind you, I t. So, equation of this current with respect to original time will be this. Now, this problem I will just tell in this fashion, instead of doing two switching, I will simply say that suppose an inductor L it was connected to some circuit and then it inherited a current. I will write I 0 minus, inherited from some other circuit this current, and then this inductor is suddenly connected here across a load resistance. Same problem I am telling, but people will be always talking in this fashion. Okay. Inductor had initial current I 0 minus 1. Now, start your time t equal to 0, it is connected to this circuit. At t equal to 0, RL is connected across the inductor with initial current I 0 minus. In bracket you can write inherited, this I 0 minus might have been inherited by this L from some other circuit, It might have inherited because it was connected to some other circuit, there was current growing up. Okay, when it reached I 0 minus. So, in this case that I t equal to 0 is well defined across at t equal to 0 RL is connected having an inductor current. So, this problem once again instead of t dash domain I will simply write this is I t and the differential equation will be plus minus this is plus minus L d I dt and this is R L I. So, so L d I L dt plus R L into I is equal to 0, and if you solve it divide by L d I L dt plus R L by L into I is equal to 0 means we have done this I L. Now, I will write t because t equal to 0 everything starts in this circuit. So, I L t will be equal to this initial current which is a fixed number inherited by the inductor into the power minus R by L into t, not R by L, it is R L by L, R L by L. Okay. So, this inductor current will decay. Is the time constant same? May not be, because your L by R L ratio may be different from L by R ratio during charging process. So, this is called discharging of the inductor. Now, these are the mathematical. So, I will say that if for this problem I want to sketch this circuit, I will say like this current waveform. This is only t, do not bring t dashed and all this 0, and here I am sketching I t. So, the inductor had some initial current t less than 0, here the current was I 0 minus. How it reached that I 0 minus? I am least bothered, because I am interested to solve this circuit and inductor started with this current. It might have grown like this in this way or some other way, I do not care. I am only interested to know at t equal to 0 minus how much was the current. At t equal to 0 I have done some switching, so that an RL is connected across L. Then I say the inductor current was like this, whose equation will be I 0 minus into, it will exponentially decay R by L into t. Got the point? And previous to t less than 0, it was this one. Got the point? So, I 0 minus keeps all the information about how current grew, we do not care that previous history is encrypted in I 0 minus 1 integral v dt. I do not care about that. If this number is there, I know what to do. Now, naturally question comes, inductor therefore stored energy. What was the initial energy then? Half L I naught minus square. This was the energy stored in the inductor. How much total energy which will be dissipated in R L? It will be this current square energy dissipated in R L will be I square. R L is the instantaneous power, energy in time dt will be dt, and this I have to integrate from 0 to infinity, because mathematically it exists up to infinity, although for all practical purposes current will eventually become 0 after few time constant, we know. So, energy dissipated will be this one. Now, I leave it as an exercise to put this value, that 0 to infinity, that is equal to W dissipated 0 to infinity, and this current square is nothing but I 0 minus square e to the power, this is also squared, minus 2 R L by L into T into dt. Now, you integrate this, but I am telling you this integration has to be equal to this one, half L I naught square, because whatever was the energy stored, that must have been dissipated. For example, you have connected a lamp here, a small lamp. What you will observe, as you disconnect this lamp across the cell, lamp will glow and its brightness will diminish as time passes, and eventually it will of course become 0, because all energy stored in the inductor has to be dissipated in R L. Why this information I am telling you? Always behind all this mathematics, if you think physically what is happening, that is much better. Okay, mathematical description is there, you choose some t equal to 0, but physically thinking is also I am trying to tell you about. Always think physically what is happening, what was the, you are doing a switching, what was the current just immediately prior to this switching. If that current value is known, you know the energy stored, and that energy you are now retrieving in some resistance, you are using that energy it is. If you like to know how the voltage across the inductance changes with time, you can also do that, because expression of I L is known, and voltage across inductance for this t greater than 0, how to find out? V L T, it will be equal to potential of this point with respect to this will be L d I L dt, is not d I dt, y d I L dt, and this will be equal to L, and I is this one. So, it will be minus R L by L into I 0 minus the differentiation of this one, I 0 minus is constant into e to the power minus R L by L into T, which will be equal to minus R L into I 0 minus into e to the power minus R L by L into T. So, this was the current, how it changes with time, And what will be the voltage across the inductance? Voltage across the inductance will be, it will have a sharp negative value going, then it will exponentially decay down to 0. What is the value of this voltage? R L is known, I 0 minus is known. So, this value will be minus R L into I 0 minus. So, voltage across the inductance can change instantaneously, current remains continuous. So, whatever was the voltage before t equal to 0 minus, I do not care, at t equal to 0 voltage has to be like this and it will go like this. In fact, voltage across the inductance, you see these two are in parallel. So, it will be equal to voltage across the, it has come correctly because of the fact voltage across the inductance is nothing but, this is nothing but minus R L into I, is not? This whole thing is I t. Why minus? Because you apply KVL here and you get L d I L dt is equal to minus R L I. So, this in short what I told about the inductor. Inductor charging is necessary to store energy, and whenever you like, you would like to use that energy. Just for fun, you do not store energy, maybe in future you will retrieve that energy. So, here was some simple circuits by which you can charge an inductor to any value of the current. Of course, to that value of the current which inductor will be able to sustain, matlab it should not exceed the rated current of the inductor. Then you retrieve that energy. Use it for some purpose, heating a coil or lighting a lamp. Not a very good example, but it gives you the idea. Okay, energy can be stored and it can be retrieved. And mind you, the last word about the inductor I must tell, and then I will stop talking. Remember few things about inductor, that is, suppose you have an inductor L, and if this is the current you are showing, as I told you, voltage across the inductor is L d I dt, is not. Now, to store energy in an inductor, what you have to do? You have to pump current in the inductor. I mean, talk in these terms, let us talk. To store energy, in an inductor, we have to pump current into it. I mean, pump current into it. I must push some current flowing through the inductor. Okay. Therefore, if current establishes, then only it stores energy. Now, you see, I wrote several times I is equal to 1 by L, then V L dt. This is the value of the current in general at any time t from minus infinity. So, to store energy in an inductor, we have to pump current into it, and to pump current into it, this quantity, see, dimensionally it is volt second, is not. Whatever will be the result, it will be multiplication of voltage into current you are doing. So, to pump current into inductor, better write this time another words, to establish current, current in an inductor, we have to spend, we have to spend volts second. At the cost of what? If you apply some voltage over some certain time, then only current will be established, L is constant. So, you have to spend some volts second in order to establish energy. And it has got a striking similarity with your Newton's laws of motion. For example, m dv dt, a mass, this is applied force and this is m dv dt is the applied force. If you want to find out what is the current velocity, then you must have to do this integration, similar equation 1 by m, and you have to integrate from infinity to t. See, do not lose sight of this fact as well. Oh, in mechanics, applied force is equal to m dv dt, v is the velocity of the mass at any time t. So, to establish velocity in a mass, you have to spend Newton second, then only, and divide it by constant mass it will be. So, sometimes F is you can correlate with voltage applied, inductance it looks like has got inertia like mass. So, inductance is often compared with mass as well. Therefore, to establish velocity you have to spend some this one. And this equation will also sometimes very useful, that is L di dt is equal to V L. It is also can be very effectively used with common sense. Suppose I say in an inductor applied voltage is like this, something very arbitrary voltage, it changes with time like that. Now, you see di dt is equal to V L by L. V L is the voltage across the inductance. This equation tells you that at any time, if the voltage applied across the inductor is positive, that is this is really positive, this is minus, then current must di dt will be a positive number. If applied voltage happens to be positive, then di dt is must be greater than 0 and current will rise. I am not telling any numbers, current has to rise, On the other hand, if instantaneous value of the applied voltage is negative, this tells me, this equation di dt will be negative, then current will decrease. So, given a input voltage waveform, I will be able to tell many things without doing any maths. Okay? And we will continue with this in the next class and starts about capacitance. Thank you.